The Riemann Zeta function, denoted zeta of s, is initially defined as the infinite sum of 1 divided by n raised to the power of s, where n ranges over all positive integers. This Dirichlet series converges only when the real part of the complex variable s is strictly greater than 1. Crucially, this sum possesses an equivalent representation known as the Euler product identity. The Euler product expresses zeta of s as an infinite product over all prime numbers p, where each term is 1 divided by the quantity 1 minus p raised to the power of negative s. This identity establishes a direct, deep connection between the distribution of prime numbers and the behavior of the zeta function. The location of the zeros of zeta of s dictates the precision with which we can predict the occurrence of primes. Specifically, the error term in the prime number theorem is governed entirely by the real parts of these zeros. Bernhard Riemann extended the domain of zeta of s from the half-plane of convergence to the entire complex plane, excluding the simple pole at s equals 1. This process, called analytic continuation, transforms the function into a meromorphic function. The extension relies on the functional equation, which relates the value of zeta of s to the value of zeta of 1 minus s. This equation involves the gamma function, specifically gamma of 1 minus s, and a factor involving 2 raised to the power of s and pi raised to the power of s minus 1. The functional equation reveals a symmetry around the line real part of s equals 1/2. This symmetry is the geometric reason why the critical line is so important.
The functional equation immediately reveals a set of zeros, known as the trivial zeros. These occur at the negative even integers, -2, -4, -6, and so on. They are called trivial because their existence is a direct consequence of the pole structure of the gamma function term in the functional equation. Specifically, gamma of s has poles at the non-positive integers, and these poles force the zeta function to 0 at the negative even integers. These zeros do not contribute information about the distribution of primes. The focus shifts entirely to the non-trivial zeros, which are the roots lying within the critical strip. The non-trivial zeros are confined to a specific region of the complex plane called the critical strip. This strip is defined by the condition that the real part of s must be strictly greater than 0 and strictly less than 1. The functional equation ensures that if s is a 0, then 1 minus s is also a 0, reflecting the symmetry across the line real part of s equals 1/2. Furthermore, if s is a 0, its complex conjugate s bar is also a 0, reflecting symmetry across the real axis. These symmetries mean that we only need to search for zeros in the upper half of the critical strip, specifically where the imaginary part of s is positive. The critical line is the vertical line passing through the center of the critical strip, defined by the equation real part of s equals 1/2. This line is the axis of symmetry for the functional equation. The Riemann hypothesis posits that all non-trivial zeros must lie exactly on this line. If a zero were found off the critical line, say at a real part of 0.6, then by symmetry, another zero would exist at a real part of 0.4. The existence of such an offline zero would fundamentally alter our understanding of prime number distribution, introducing larger and less predictable error terms in counting functions.
The Riemann hypothesis, proposed in 1859, states that every non-trivial zero of the zeta function has a real part equal to 1/2. This is the most important unsolved problem in pure mathematics. If proven true, the hypothesis provides the tightest possible bound on the error term for the prime number theorem. The prime number theorem estimates the number of primes less than or equal to x using the logarithmic integral function. The hypothesis guarantees that the error in this estimation grows no faster than the square root of x multiplied by the logarithm of x. This precise control over the error term is the primary mathematical payoff of the hypothesis. The hypothesis directly impacts the distribution of primes through the counting function pi of x. Without the Riemann hypothesis, the best-known bound on the error term is significantly weaker, allowing for much larger fluctuations in the density of primes. The hypothesis ensures that the primes are distributed as smoothly and regularly as mathematically possible. Furthermore, the hypothesis is equivalent to specific bounds on the Mobius function, mu of n. Specifically, the statement that the sum of mu of n up to x grows no faster than x raised to the power of 1/2 plus epsilon is equivalent to the Riemann hypothesis.
The distribution of the non-trivial zeros exhibits a striking statistical pattern that connects number theory to quantum physics. The Hilbert-Polya conjecture proposes that the imaginary parts of the zeros correspond to the eigenvalues of a specific self-adjoint operator, essentially the energy levels of a quantum system. While the operator itself remains unknown, the statistical spacing between the zeros precisely matches the Gaussian Unitary Ensemble, or GUE, distribution. This distribution describes the energy level spacing in complex quantum systems, such as heavy atomic nuclei. This unexpected correspondence suggests a deep underlying physical mechanism governing the location of the zeros.
Extensive computational efforts have verified the Riemann hypothesis for the first several trillion non-trivial zeros. These calculations use algorithms based on the Riemann-Siegel formula, which provides an efficient method for calculating the value of the zeta function on the critical line. The verification process confirms that all tested zeros lie exactly on the line real part of S equals 1/2. However, verification of a finite number of zeros does not constitute a proof. A single counterexample, a zero found off the critical line, would immediately disprove the hypothesis and revolutionize number theory. The Riemann hypothesis is one of the 7 Millennium Prize Problems established by the Clay Mathematics Institute. A successful proof carries a $1 million reward. The implications of a proof extend far beyond pure mathematics, impacting cryptography and computational complexity theory. For instance, the efficiency of certain factoring algorithms and the security of public key infrastructure rely on assumptions related to the distribution of primes, which are formalized by the hypothesis. Proving the hypothesis would solidify the foundation of modern number theory and provide definitive answers regarding the ultimate randomness and structure of the integers.